Hi, Samantha. How are you doing?
Hi, Professor. I'm doing good. How are you?
Thank you. We'll start in a few minutes. Okay, so you can check it out the assignment in the notes. Let me fix this due date. Sorry, it's it's past. Okay, we'll start in about a minute. So check out your notes and your assignment. Okay, so we're gonna go ahead and get started. So just to preview, for this week, we are gonna work on chapter 12 and 13, which covers induction and recurrence. We are gonna do a lab on Fibonacci in C++, and we're gonna look at recursive functions a little closer. I know we've been working on it for a while now. So in addition to the assignment in the lab, we are going to prepare for our next quiz, which is going to happen next week. And sorry for the due date. I thought I fixed it, but I just modify it. So this is not going to be due until the 24th, which is the end of the week. If you have time, please look it over. This is going to help you get your quiz review. And also, we are going to have a game that's going to be for an e-gift card from Amazon for $25. That's going to open next week. And if you attempt it, you can also get extra credit. So for the highest score, I will send out the e-gift for that. So make sure that we look over your homework assignment and get that done. If you already did that, then that's fine. But if you haven't, you can work on that. Okay. I will also open the course project module, which is going to be next week. I'm going to open it next week. It's going to be due at the end of the semester. So you will have about 6 weeks to work on. In addition, I just want you to know that we are going to have about 3 more weeks of lecture and lab. Okay. I'm going to do a final review. Maybe sometime in week 14. So either 13 or 14 following our lectures. And I want you to use the time to work on your course project after we finish with the lecture and the lab, because by the end of week 12, we should be covering all the chapters in the text, except for 4, because 4 is very simple and we already passed 4, but we're going to come back to chapter 5 in unit 11. And we are going to have one more quiz, which is going to be on the last few chapters. Your final exam is going to cover all the chapters that we've gone through from the beginning to the end. And we are going to have to submit our course project. You do have an option to work in team, and I'll talk about it more next week. So we would need to start preparing. I know the program doesn't take you very long to do, but I am aware that you have other classes to worry about. So I want to give you more than 4 weeks to work on it. In the past, I've only done it in 4 weeks, but so that way you can build on it a little bit at a time. And then before the final week, you should be able to get it done and submit it. So do not wait until the last minute, because there are a lot of different parts to the course project. And so you are going to be super behind and stressed out as you are preparing for final exam. So do not wait till the last couple of weeks to work on it. Okay, so give yourself some time to work on that, as I would give you time that we normally would be. After the final review, I can make myself available if you want me to meet with you and look at the project that you're working on, and we can talk a little bit more about it next week. So that way, if you don't understand something, if you need additional approaches, you know, but in any case, you need to turn in something for your project. Okay. All right. So let's talk about 12 and 13. And we are going to do the assignment as usual. So in chapter 12, it's going to go over math induction, and we are going to use inductive reasoning. In the extension of this, not so much as in some math courses, but we want to get the basics. And then we want to be able to build on that. So in the case where we need to solve a problem using programming language, we would know how. So math induction is a technique where we need to prove a specific statement about natural numbers, and we can apply different approach in how we would solve this or solve the problem. So some of the problems that you would see in general for using mathematical induction is the Hanoi Tower, the falling dominoes, logical puzzles, which you see quite a bit in games. And it is a way for us to provide mathematical statement by establishing the base case. So if we can prove that if the first case is true, then all the other cases based on the given scenario would be true too. Now, inductive reasoning is a way that we can reason in which premises are viewed by supplying evidence for the truth of the conclusion. Okay, so we are going to build out the case, and we are going to write out the proof, and we are going to provide inductive reasoning in the process. So looking at the prior theory, where we cover Gauss trick, in that you learn how to calculate the partial sum by looking at the first, the last number, and then the total number of terms. So we can verify that the truth by noticing the pattern of the sums from the first to the last element. And we would provide the proof in that we have seen or established a pattern that would be as important to that particular problem. So here I highlighted the 2 steps that you need to know for induction. The first step is you need to build a base case. And this is to prove based on the given statement for the first natural number, whether that is 1 or 0, right? So that's going to be our base case. So that's the first step. The second step in induction is to prove that the given statement for any other number implies that would be the next natural number. Could be 2, 4, 100, etc. That would be true. Okay. So the authors provide also the summary of the 2 steps. Okay, base case, and then we would do an inductive step. And to also come back to our sets notation, I added the table for some of your set notation, so you know how to, you can review that, know how to read it. Okay. So what we want to do for the first question is we want to define what is mathematic induction principle. And mathematical induction, we can define it as a technique used to prove specific statements about natural numbers very directly. And this comes from the notes. It can be applied to a wide variety of circumstances. Mathematical induction is a way of proving a mathematical statement by saying if the first case is true, then all the other cases are true too. So you can simply clip that from our notes, or you can type it. Okay. And this is important because when you're working with writing your C++ program for the project or in future classes, you have to really think about how you would procedurally solve and improve, right? Solve the problem and be able to provide evidence or proof based on your case. Question. Okay, so before we do number 2, let's take a look at what the notes are going to give us. So here in the first example from number 12, it gives you a case or a problem. So we wanted to show that Gauss trick, right, would be used for summing up our sequence, which is arithmetic. And so we want to show for our base case for the n is 0. So what we want to do is we will plug in 0 for n, and we will try to solve it. So when you plug that into the Gauss trick equation, you would have 0 times 0 plus 1 divided by 2. Would n is equal to 0 is going to be our base. So then we know that whenever the equation is true, we can say that n can be any value. It could be a value that represents k, and it would be any value subsequently. So k plus 1. Okay, so if that's the case, then we would plug in k as the value for n. And then we would also represent k plus 1 for any other subsequent value. So then we would plug that in here, as I would have the blue arrow pointing to that. and then we would solve it. Okay, so then we would see that it shows that when you simplify this, it would show that it would be equal to n times n plus 1 divided by 2. Okay, so the example in the book, it gives you the sense where, okay, you understand what k would be representing any value and k plus 1 will be any other value or the next value after k. But let's bring it to the real world scenario. And I know that some of you don't ever use stamps, right? But for those of us who have used stamps, and your family member probably use stamps to send letters and postcards and Christmas cards and such. But before the forever stamps, they used to have a certain value in stamps. So postage, let's say that you need to have a postage that will be 12 cents or more, okay, to send a letter. And the way that you can combine your combinations would be 4-cent stamp and 5-cent stamps. So we have to have a statement to begin our induction. So our statement is that postage of the n cents can be formed by 4 cents and 5 cents. So how did I come up with this? Right, from this right here. Now we want to claim that the first part is true, that for every amount of 12 cents or more, we can combine 4 cents and 5 cents to make it 12 cents. Okay, so your claim would be n is going to be greater and equal to 12, right? And that's come from here. And in that, we want to show that P of n is true, which is our statement. We can form 4 or 5 cent stamps to make it 12 or higher. So this is a strong induction proof for n, where our base case would be n is going to be equal to 12, 13, 14, 15. Okay. So why do I start at 12? Because n is going to be greater and equal to 12. So 12 cents or more, remember? So is 13 cents higher than 12? Yes. 14, 15. So we can start looking at combinations to make 12 cents. That will be n is equal to 12. So here we can say n is equal to 12, right? So that means that we can form a postage of 12 cents by using 3 of the 4-cent stamps. Then when n is equal to 13, very similar to what we've seen last week, we can have 2 of the 4-cent stamps, which gives us 8 cents, plus 1 5-cent stamp, which gives us 13 cents. Okay. Now, when n is going to be equal to 14, right, we can have 2 of the 5 cents, which gives us 10 cents, plus 1 of the 4-cent stamp, which gives us 14 cents. Okay, now we got to do the last one, which is 15 cents. So when n is equal to 15, then we simply use 3 of the 5-cent stamp. So as you can see, we simply, right, take each of the base case where n is equal to a certain value, and we want to be able to prove that P of n is true. Okay, so once we write that out, we see that all of these tests that we have put it through when n is 12, 13, 14, 15, they are all true. Thus, P of n is true for all elements of the base case. Okay, so establishing the base case is very important. That's the first step. In the induction step, you need to write out the induction step. So let's say that I need to have n is equal to 15 or higher. Then we would assume that P of k is true, as we mentioned that P of n is true for the base case. So if we place k between 12 and 15, we would know that k cents can be formed by 4 cents and 5 cent stamps. That's going to be your induction hypothesis, right? We want to predict that this would be true for the k value. So to form the postage of n plus 1 cent, we would then use the stamps to form a postage of n minus 3 cents, because this comes from the induction hypothesis. Okay. So we can also prove that anything subsequent to our base case, 15 or higher, because if you look at 16, we can do what? Four of the 4 cent stamps. 17, we can also do the combination. So we would then be able to prove that P of n plus 1 is also true. Okay. So, and this is important because we want to come back to what was the statement earlier in our claim. Okay. So let's do an exercise so you can get a clearer picture. Number 2. It tells you to use the induction principle to prove that 2 to the n is going to be less than the factorial of n. For n is greater or n equal to 4. Okay. So when we look at this statement, right, we need to prove this, and it's given us the value. So this is our base case. So then we would write out, first we write out our base case. So for the base case, you have n is going to be equal to 4, right? That's where you start. After you put down n is equal to 4, then you're going to plug in 4 for the n value. So I would have 2 to the n, so 2 to the 4. That gives me 16. And I wanted to test it now to see if it's less than the factorial of 4. So a factorial of 4 is 4 times 3 times 2 times 1, which gives me 24. So therefore, this is true. Okay. So what we did there was we established the base case. We used that value to plug into our equation here, which is in our statement for proof. And we show that for the base, that's true. But we have to also prove that when n is a greater value, anything that's larger than 4 is also true. That's the requirement. So part 2 to this is your induction step. Okay. And this can be a little lengthy, right? So we say that n can be k, and k is greater and equal to 4. So we would say let n equal to k, and k is greater and equal to 4. Okay. So we can assume that P of k is true. that is 2 to the k is less than k factorial. This is your induction hypothesis when you make that assumption. Then we want to prove that p of k plus 1 is also true. That is 2 to the k plus 1 power is less than k plus 1 factorial, right? So we simply take the k plus 1 and replace it with the n. Okay, as we did with the k, because k could be any value, and the value after k would be k plus 1. So then we would take our induction hypothesis and we restate it, and we would test it with our base value, which is what we've done already up here. So we know that that is true. And I type that out in blue, so just in case, right? 2 to the 4 is like we multiply 2 4 times, and then factorial of 4 is 4 times 3 times 2 times 1. Any question? Okay. So then we would apply the exponent law. So here is where we're going to go ahead and multiply 2 to both sides, because algebraically, if you do it to one side, you got to multiply it by the other side to achieve the balance, right? So why am I multiplying by 2? Because it's 2 to the k power. So if I multiply it by 2 to the both side, okay, so here it tells you that multiply both sides by 2 as k to the k, or 2 to the k plus 1 is 2 times 2k to the k power, right? That's the exponent rule, is that when you have any value that's subsequent to k, it simply is like multiplying like this, right? So it's like saying 2 to the third plus 1 is like we're multiplying another 2. So that's why we'll multiply 2 to one side, we have to multiply 2 to the other side. Okay, so this is the reason why I'm multiplying 2. Because it's k to the k plus 1 as an exponent is equivalent to 2 times 2k. So as we multiply 2 to both sides, we then also plug in the 4, right, for k, because that was here, to see if that's true. So here I would get a result of 32, which is less than 48. Check, true. Okay, any questions so far? All right, next step. Now, what we need to do is we need to prove this part. Okay. So here we would say that 2 times k factorial is less than k plus 1 factorial. Okay, because k plus 1 is larger than 2. So that means that when I plug in the 4 in place of k, I should be able to get that as true, right? So 2 times 4 factorial, which is 48, and 4 plus 1 factorial, which give me 5 times 4 times 3 times 2 times 1. This give me what? 20, 40, 120. So 48 is definitely smaller than 120. That check's true. Okay. Then we also need to prove that k plus 1 times k factorial, which is going to be any factorial subsequent or the next value of after k factorial, this is what it means, right? Is equal to k plus 1 factorial. And this comes from the factorial definition. Okay, the value that's adjacent, that's after k, is k plus 1. And so when we write it like this, right, you understand that that's k plus 1 factorial. That's going to be the same as k plus 1 times k factorial. So when we plug 4 in for that, we would have 4 plus 1 times 4 factorial equal to 4 plus 1 factorial. And you multiply that out, which this gives you 120. This is also 120, so that's true. So throughout the induction step, right, we have proven that our claim is true. Okay. We have proof using factorial definition. We have proof using exponential definition, right? We also have proven, yeah, there were a couple sections from the factorial. So based on that, we have proved our claim is true. So any value after 4, 5, 6, 8, 11, etc., it should apply, right? Should be true. Any question? Okay, no question. So are you expected to write this out for the final exam? No, but I'm gonna expect you to know how to do induction, right? As you would get some questions on the final exam relating to this particular chapter. Okay, in other courses, right, you have to show all your proof. Okay, any question? No, all right. Want to try another one? Let's try another one so you can get a hang of it. Some of these are longer than others, right? Just tedious that you have to write out. And I try to make it as clear as possible. So when you, of course, you can just put down your answers in the steps and simplify it. But if you know how to do that, but for the students that don't know how to do that, right? Little bit of notes also help. So your assignments is for you. Like I said, make sure that you include the things that would be relevant to you. And that's important. Okay, not just to put down the answer. All right. Next one. Let's try a different one. We're going to look at number 3. I'm just going to show it so you can see. This one's a little different than that one, the last one. So we want to use induction principle to prove that 3 to the n minus 1 is a multiple of 2, right? Which we normally see that as an even value, right? For n is greater than or equal to 1. Okay, so the statement that's given there, we already have a base case, which is here. And we need to prove this. Okay. So we would then first establish our base case. Our base case, n is equal to 1. Right? Let's plug in 1 and see if it works. 3 to the first power minus 1 gives you 2. Check. Is it an even number, multiple of 2? Sure. What if we plug in number 2, for example? Right? 3 to the second power minus 1 gives us 8. It is multiple of 2 as well. So we have our base case. Then we're going to go into induction steps. And the first part of the induction step, we want to make n equal to k. So we can say let n equal to k. And let k be your base case, which is greater and equal to 1. And then we're going to state our hypothesis, making an assumption. So we can say, assume that P of k is true. That is 3 to the k power minus 1 results in an even number or a number that is multiple of 2. Okay. So this is our IH. Then our claim, we want to prove that P of k is true. That is 3 to the k plus 1 minus 1 results an even number or a number that is multiple of 2. So anything greater than 1, right? That should be true. So we would start with our induction hypothesis, which is here. We would then take 3 to the k power minus 1, and we simply plug in our base value, which is 1. And you saw that happening here. So 3 to the first minus 1 gives us 2, which is true. Then we want to use this, right? This is next. So 3 to the k plus 1 power minus 1, that is earlier you saw in the previous one by the exponent definition, then we would have 3 times 3 to the k minus 1, right? So if you plug in 1 for k, that gives us 3 to the 1 plus 1 minus 1. That's going to be equal to 3 times 3 to the first minus 1. Oops, which is true. So A is equal to 8. Any questions so far? Then the next step, and this is usually the student, they get confused about that. Remember that our claim, this part we have to show, right? It is a multiple of 2. Okay, because so far what we've been doing is we were just showing what k and k plus 1 potentially could be, right? And we show that this is 2, this is 8. So we would take this claim right here, which is 3 to the k plus 1 minus 1, and we want to show that it is a multiple of 2. Continue from the previous term. So anything in the subsequent, right, it would yield also an even number. So 3 times 3 to the k plus 3 to the k minus 1. Where is this? Right, that's from the previous term. So then I would plug in 1 for k. So 3 to the second here minus 1, which gives me 8. 9 minus 1 is 8. And then I would multiply out. So 2 times 3 to the first plus 3 to the first minus 1, which is also 8. Check. So we have proven that our claim is true. Any question? Okay, no question? We don't have that many exercises to do today. It's just each exercise takes a little bit longer today. Okay, just to write out everything. Okay, so only 2 pretty easy ones at the least. Then we're going to talk about chapter 13 next, which is recurrence. All right, no question. So the book gives you additional example. You should explore it, right? The way that they write out their base case for the induction, and so on. I just felt like, some of the explanation, it could be synthesized a little bit. So I was hoping that when you do the assignments with the steps that you see, that's going to help you see it a little clearer. Okay. So I use something similar to this right here in the number 3. Okay. Then chapter 13, this is on recurrence. So in the last few weeks, I think we started looking at some of your recursive functions, how to really use that with your search sort, and you see it in other areas, right? And sometimes we would use iteration, and other times we would use recursive function. And mathematically, recurrence is just a formula that would specify the running time of the algorithm, right? Based on the input or the n elements. So your T of n is going to be the function of the running time on a smaller number of elements. Okay. So the ones that we've done was merge sort. We can recursively call that function on the first and the second half of the element. And then because merge sort is divide and conquer, right? So as it divides it into half, and then when you get to the portion where it would start merging, right? It would sort and then merge. Okay, so the lower value is going to go to the front and it merges. So as it merged back, it will be subsets or subgroups. And that's going to be returned by your recursive calls. Okay. So as you can see, when we divided your array into halves, and if we continue to do so, you would see that n divided by 2 is going to be used at the running time of the merge sort, as it needs to cut the array into 2 portions. Okay, halves of the elements. Then for in the step 2, with the number of operations, it would then need to sort the groups and put it back into the total size again. Okay. So as it cuts it into 2 subarray, we would see that it needs to do it twice for the T of n divided by 2. So that will be represented by this, right? Because we need to merge 2 of the subarray that we cut into half together plus n. So the way that the text suggests it is that it is a good practice to first rewrite your recurrence with the recursive component last. Okay. And we want to look at the equations based on what that placeholder, the star, would be. Okay, so for the merge sort, you would say n plus 2 times t of n divided by 2. And as it divides it further, you would see that it's going to be the subsets of the previous halves and so on. So then we would increase the exponent for the n divided by 2, as well as 2 to the 2 that we multiply to those halves. Okay. So the way that the text present this is more of an illustration on how you would go step by step to really establish, right, what you see with the merge sort. Okay, so let's do some exercise on recurrence. Next question. Define recurrence. A recurrence relation is an equation that expresses each element of the sequence as a function of the preceding ones. Okay. Yep, no problem. Okay. So the definition for recurrence would be the recurrence relation is an equation that expresses each element of the sequence as a function of the preceding ones. So we're going to look at the previous value in that element, right, to be able to calculate the next. So let's put that into numerical expressions for number 5. For number 5, it asks you to find the recurrence relation and the initial condition for 1, 5, 17, 53, 161, and 485. So by definition, we know that recurrence relation tells us how to get from the previous term to the future terms. So it builds on the value of the previous term. And that's what you're going to see with Fibonacci in the lab. Okay. And you don't have to do the table. I just wanted to show you the table so that way it's easier to see. So when we look at this, when we compare the values from 1 to start, right? How it got to number 5 is going to be that it adds 4, right? So if we take 5, subtract 1, we see that the difference is going to be 4. If we take 17, subtract 5, we're going to see the difference is 12. And so on. So we would take the next value, subtract the previous, we would get the difference. So then we would need to take a look at the difference as a sequence. So we can see that the difference of the original sequence would represent there is a common factor and it's going to multiply it by a specific value. 4, 12, 36, and 108. Okay. There is a growing by the 3 as a common factor. So if we think about that, going back to the original sequence, right? Is there a growth with a common factor of 3? So if we take 1 as the first value in that sequence, which is here, and we multiply it by 3, we have 3. If we take 5 and multiply it by 3, we get 15. We take 17, multiply it by 3, we get 51, and so on. So when we look at this, right, compared to the original sequence, it would appear that there would be 2 less than the next term, right? Because 3 is going to be less than 5, and then 15 is less than 17 by 2, and so on. 51 is less than 53, and you start to recognize the pattern. So we can say that 2 of n is going to be 3 times a of n minus 1 plus 2. Why is that? Because 3 is a common factor, right? We saw this here, and we saw this here. And if we take that 3 and we multiply it by the previous term, how do we get from here to the next term? Is that we have to add 2 to it, right? Because if I take 3 times 1, I get a 3. In order to get to 5, I have to do a plus 2. If I take 3 times 5, I get a 15. In order to get to 17, I have to do a plus 2. So we can define what a of n would be. A of n is going to be our common factor times the previous value plus 2. And this is the expression for your recurrence. Okay, so I wrote that out. And this is going back to what we've seen in chapter 11 as your arithmetic progression. Any question? So on the final exam and future quiz, you are going to be presented with a sequence like this. It's going to ask you to identify, right, what AFN could be in the recurrence relation format. Okay, so it's because it's multiple choice, you have to select the right choice. So how do you approach that? You take a look at the sequence, okay, and you would identify the difference between the numbers. And then from there, you would try to identify the common factor. You use that common factor and you apply it to your base number, which is the first value. And you are going to look at the distance between that result and the next value. That's how you're going to be able to write it. So progression is going to fall into 3 categories that we talked about last week, right? You're going to have arithmetic progression, geometric progression, or you would see as quadratic progression. So our recurrence relation can be expressed as this. So how do I get to A of n? I would take 3 times A of n minus 1 plus 2. Question. Okay. So can I move on to 6? You're good? Okay, here we go. All right, let's solve for 6. Use recurrence relation concept to check that A of n is 2 to the n plus 1 is the solution to the recurrence relation. A of n is 2 times A of n minus 1 minus 1. So the previous value here, where A of 1 is going to be 3. Okay. So here it tells us that we have A of n is equal to 2 to the power of n plus 1. And we need to check that for our recurrence relation, A of n is 2 times the value before A of n minus 1, where A of 1 is 3. So if we simply take this first equation and we plug in the value for n starting with 1, right? We would build out a sequence 3, 5, 9, and 17. And so we know that 3 is going to be the first value, which is A of 1. So for the second part to this, we need to verify that this is true, the recurrence relation. So then we would have A of n is 2 times the value before A of n minus 1. Again, we're going to plug in A1, A2, and A3. And I already established that here So I simply plug that in, right? So if A of 1 is 3, then A2 is 2 times 3 minus 1, which is 5. And then A3 is going to be 2 times 5. That's the value, the previous value, minus 1, which is 9, and so on. So A4 will be 2 times 9, right, minus 1, which is going to be 17. So as it checks out that you're going to have the same sequence as you've seen when you solve for A of n, we can say that A of n is 2 to the n plus 1 is the solution for the recurrence relation A of n equal to 2 times the prior term to A of n minus 1, with A of 1 is 3. Okay, so this we only need to verify by plugging in the value to determine if the sequence is exactly the same, which it is. So when you take this into C++, right, you would then include algorithms so you can implement the equations. But when you append this, you can put the value into an array. And you can start with, and you don't have to have an array right off the bat, right? You can build out, you can do dynamic array as you would append the value as a sequence. So you would start with A of 1. It's going to take that, right? It's going to plug it into the equation, this equation, to multiply by that minus 1, and then append that to the value subsequent to 3. And so you can build out your array so you end up with an actual sequence. You would check that against the other sequence, and you would then have, right, the if statement. If the elements for this is equal to the element of this is true, then check, right? So pretty straightforward. But we have to understand how to solve it mathematically to be able to implement the procedure in the programming. Question. So leaving this class, what I want you to see is when you're looking at the problem, right? If you solve it mathematically, you should be able to see it, how you would solve it, C++ or programming wise, okay? Because we try to do the parallel so that that way you can see it. And yeah, we can just write a recursive function and be able to do that. Or we can write a function and then, and then build in a loop. And so it can iterate. We saw some of the solution that way. Question on 6. Okay. Time flies. We're more than halfway done now. So, all right, let's look at number 7. So like the last one, we're going to solve the recurrence relation. A of n is going to be A of n minus 1 plus n. And your initial term, A of 0, is 4. And we try to mimic what we would see in an array, right? A of 0 is 4. That's your first term. So we have the base number. We're going to build out our sequence. So then you will plug 4 in. So to get A of 1, you're going to take 4 plus 1. You're going to get a 5. And then A2 is going to be 5, which is the previous value, right? Plus 2, 7. Next, A3, 7, previous value, plus 3, equal to 10. So the next step is to look at their difference, right? My sequence. I have 4, 5, 7, and 10. Okay, at least partial anyway. So we would see the difference between the terms. If you take A1 minus A0, you get a 1. 5 subtract 4 is 1. Then you take A2 minus A1, 7 minus 5, you get a 2. And you take A3 minus A2, 10 minus 7, you get a 3. So now you start to see a pattern, right? This progression there. Okay. So we can see that A of n minus A of n minus 1 is n. 1, 2, 3. Questions so far? Okay, easy, right? Now we are going to do sum on both sides. So if I take this, right, the difference, and I add it with the next difference, and I add it with the next difference, and so on, right? That will be 1 plus 2 plus 3 plus 4 plus n. So I can say that A of n is equal to A of n minus 1 plus n. Algebraically, you can move this by adding it to both sides, right? That's why I put find sum to both sides. If you take this and you plus A of n minus 1 here to cancel it out, you add it over here, you have A of n is equal to n plus A of n minus 1, which is this equation. And there we have it, right? So if I take, for my A of n, if I take n times n plus 1 divided by 2 plus A0, and I plug in the 4 for A0, okay. Let me move this down. Second. Then we would have a test condition. Okay, so here I would have A of n is equal to n times n plus 1 divided by 2 plus A of 0, and we know that A of 0 is 4. Then our test condition, when we plug that in, or your A of 1 is going to be 1 times 1 plus 1 divided by 2 plus 4 is equal to 5. So the solution for your recurrence relation subject to the initial condition is A of n is equal to n times n plus 1 divided by 2 plus 4. This one's a little harder than the last one, but Okay. Questions? No questions, huh? Yep, that's all we have to do today, which is only a few questions for our assignment. But I encourage you to practice, right? Know how to do inductions, know how to be able to write out the induction step. Looking at recurrence, we are going to continue some relations material in the future class, but we're going to come back to some of this as well throughout our labs. But this week we are going to do Fibonacci, which we are going to write recursive functions in Fib. Okay. And next week we're going to cover graphs. And then we are going to go into encryption. Okay. So if you like to pre-read for the next week in Unit 10, that will be Chapter 16. Okay, and we're going to take a look at different type of graphs, as one of the project also require graph knowledge. And then we'll take a look at project options on which one you wanted to do, and then talk about the requirement next week. Okay, that's all I have for you today. And so if you're finished with your assignment, you can submit that on Canvas. And then you can type your name into the chat. I'll stick around for question. Let me stop recording.